Hey guys, welcome back to our applied mechanics. This is part 2 of our friction or frictional resistance module. If you just hopped on here, I'd highly recommend that you start with part A or part 1, which essentially covers the basics, the introduction. We will be getting certain angles and components and why we would be reasoning the way that we are. So on today's video, or on this specific video, we will start looking at some examples so that we can try and understand this module better. All right, so we're going to start with example 1. All right, I'm going to try to list or write out some of the information as I read it, but assuming a lot of it will make sense as we go along. Right, it says a body with mass of 80 newtons rests on a horizontal surface. Assume a coefficient of friction of 0.25 and calculate the force applied to the body at an upward angle of 30 degrees to the horizontal. And it's a two-part question. Part A, calculate the force required to just pull the body over the surface. Part B of the question says calculate the force required to push the body over the surface with a constant velocity in each case. Okay, so we have a body. And one key point we found in this question is that it is being pulled over a horizontal surface. So it's flat, it's not at an incline. We have the body and they say it has a mass of 80 newtons. Okay, rests on a horizontal surface and we assume a coefficient of friction of 0.25. We can just have that on there so we don't forget it. And calculate the force that will be applied to the body at an upward angle of 30 degrees to the horizontal. Okay, I might need to move that coefficient. It's in the wrong place. Okay, let's move you. Sharp. Then we have a force that is being applied to the body at an upward angle of 30 degrees to the horizontal. So we have, since it's a two-part question, we can draw out two diagrams so that we can try and understand or decipher what they mean. But for purposes of part A of the question, they say we need to calculate the force required to pull the body over the surface, right? So for starters, we can just understand where our point of action is. They say it is at a 30 degree. So we can have our 30 degrees over there to the horizontal. And since it's pulling, it will be essentially in this direction. You can even decide to put it on this side. You can put it here and say it's pulling that way. It's not really, cast in stone that it has to pull it to the right. Right? And since we have this, there's our 30 there. Okay, I'm messing it up. There's our 30 on there. Right? Then it's a force F. We don't know the magnitude of this force. It's what we're trying to calculate. So for now, our force will be a force F, right? So remember, by virtue of knowing that you are trying to pull a body across a surface, and what we have dealt with or what we know so far is that your frictional resistance acts in the opposite direction to where your force is going. So if you are pulling a body to the right, your frictional resistance is going to the left. We just don't know the magnitude up to so far. So our diagram will equally have your frictional resistance on here. It's pushing in the opposite direction because that is the force that is resisting movement. It's a force that wants to keep your body in the same place or for it to move in the opposite direction. All right? Then now we're going to go back to our steps. We had some steps on how we go about dealing with this. So step 1, you sketch. We've done that. Step 2, replace your forces with your components, with the perpendicular as well as your parallel components. Okay, so remember that our components are there essentially to try and, I feel like my screen is too busy. Sorry. Remember our components, we are essentially trying to represent this inclined line on there. Okay, so when you're now looking into your components, don't look at anything else. Look at the line that is at a specific angle, and you're looking at expressing that in terms of the vertical and the horizontal components, or the vertical line and the horizontal line. Okay, so you can have it on there. That's our parallel because it's parallel to the surface. That's our perpendicular one. They're pulling away because our force, we have assumed that it is pulling away. If, for instance, we were dealing with one that is pushing in, so we would have a body on here, and let's say the force is pushing the body like we will do in part B, then obviously your components have to align with that, and essentially they would be pushing into that as well, all right? But we're not dealing with this one just yet. Okay, then our components. Remember, we have our angle 30 here. Our angle is 30. And if you try and remember what we were dealing with in our previous video, our SOHCAHTOA, okay? Our angle or our angle of reference is reference 30. We are essentially trying to represent what would be on the opposite side and what would be on the adjacent side. Our adjacent side is our x, our opposite side would essentially be our y, alright? So which of these formulas, which of these quick equations or formulas would help us to express our y as well as our x? All right, so already we kind of have this line F on here. We'll take it as a known, even though we don't know the magnitude yet, but it's a known thing that we have. Okay, so this F, we know it, it's there. Its value for now would be F. So what we don't know would be our X and our Y. Okay, so you look at these formulas. This is the sine, this is the cosine, this is the tan. Okay, then we're trying to get the opposite. We have the hypotenuse, we can use the sine. 30 degrees, because we already know the angle, would be your opposite over your hypotenuse. Your opposite is your y, your hypotenuse is your f. Okay, so now we are essentially trying to express our y in terms of f and your 30 degrees or your theta. So y would be your f sine theta. Okay, so your vertical component or your perpendicular component in this instance would be that y. Okay, then similarly we're trying to express x in terms of your f and your 30 degrees as well. So your cos of 30 or cosine of 30 would be your adjacent over your hypotenuse. Your adjacent is your x, hypotenuse is your f. So x would be your f cos 30. Okay, why is this important? We are now trying to express our components, right? So then you can plug it back into the diagram to make it look real, or if in case of your work you would have already drawn it, then that's fine. You can just simply redraw it or just show it. Try and show. Okay, so our x here is our f cos 30, then our y is our f sine of 30. Okay, then now we have our components. That is step 2. Then we're going back to step 3. We have this formula to now make use of. Okay, so step 3, we can say our frictional resistance as our perpendicular forces multiplied by our coefficient of friction. Okay, remember our coefficient of friction was given as 0.25, so we have that. Then now we need to essentially figure out which one of our forces here are our perpendicular forces. Okay, so how I normally like to simplify this, I'd say forces acting on the body should equate to your friction resistance. Doesn't need to be a long sentence like that. Okay, then the forces acting on your body, we'll say they're your Fx, then your friction resistance is your Fu. Okay, it might work to try and break it down as you go along. Okay, then now we're looking at our body. Okay, here's our body. Here's our body. Okay, then we'll say when looking at our body, which has a weight of or a mass of your 18 newtons, right? What forces are acting on this body? This is our body. Okay, let's focus on this body on here. What forces are acting on the body, and how you can essentially break it down further. Your friction resistance will be what's trying to keep the body stationary. It's trying to keep it in the same place. This is essentially trying to either pull or it's trying to push on the body, but it's trying to move your body. Okay? Then we'll say your Fx should be equals to your F mu. Then for your frictional resistance, you already have the formula. You can just plug and play on here times your coefficient. Okay? Then your Fx, this is the part where it normally gets a bit confusing for some people because you have a range of forces which it looks like they could be acting on it. Okay? So remember, on our frictional resistance equation, I want us to break this down a little bit. Let's go here. Let's have a breakout session for 2 seconds, right? And I want this diagram to still be visible. You have your body on here. And essentially now we don't even pay attention to that force that was pulling it at an angle. We're gonna disregard it for now. What we have now would be a parallel force, your F cos of 30, and your perpendicular force, your F sine 30, and then you have the mass, which is your 80 newtons. And remember, there's that whole mg thing that you need to deal with. Okay, then we would have our frictional resistance. Okay, this is essentially now the forces that are acting on your diagram. These are the forces that you will be considering. But remember, from your equation, your friction resistance equation, it takes into account your frictional forces times your coefficient of friction. Okay, and looking at your diagram, your F sine 30 essentially is acting perpendicular to your body. It is a perpendicular force. Okay, unlike your F cos 30, which is essentially working to pull the body, right? Then you have your frictional resistance, which is working completely against your F cos 30. Okay, I hope it's not confusing. I hope we're still together. I hope we're still together. Right? Then you have your weight or the mass of your body. And remember, this will exert a force. Okay? It also exerts a little bit of a force because it's got a mass. This also acts perpendicular to the surface. Okay? Because it's the mass of your body acting perpendicular to the surface. Alright? I don't know if this adds more confusion or it helps to try and explain, but the reason why I'm breaking it down further is because when you need to now plug them into this equation on here, you essentially need to differentiate between the forces that are acting on the body, that are making the body move, and the forces that are keeping the body in the same position, or the perpendicular forces that are helping the body stay in the same place. Okay, so when we are considering our Fx, or forces that are acting on the body, remember we said this essentially is acting on the body. It's pulling the body, it's helping the body move. This, we said, it's helping the body stay in the same place. This, we said it's helping the body stay in the same place. This, we said it's helping the body stay in the same place. Okay, then we go back into our equation. For our Fx, we'll plug our F cos of 30 on here. Okay, then now we're going to break it down further. Since we already have our coefficient of friction, we can just substitute on there since these are our known points. Okay, now we're trying to essentially get to a point where we're able to solve for this, because at the end of the day we want to know the force of F. We need to understand how is this F acting and watch the story with our F. Okay, alrighty. The next, you can assume your direction. By now, we already know that we're acting on something that is pulling on the body. So anything that's moving in the opposite direction would then assume a negative sign. Okay, we can treat it as such, right? Then we can just decide that from this diagram over here, we can just decide whether your upward is positive or negative, whether your left is positive or negative, okay? But for purposes of this calculation, would say that our right is positive because it's pulling the body, and we'll also say that our downwards is positive because that's in the direction of your gravitational pull. All right, now we need to go back and plug and play. Our F costs 30. Now we need to essentially plug in or attach the perpendicular forces that are acting on the surface, acting on the body as well. Okay? Then remember we had this 80 newtons. It is a perpendicular force. It's acting directly onto the surface as a result of the weight that we have. Okay? Then since it's acting downwards, it'll be positive. Then now we need to take into account this y, but it's in the opposite direction, so that's why it's our negative. We now have our F sine 30. Okay? These are the forces acting on the body. Just double check if you've included everything. If you have, then you can then just multiply by the coefficient that we're given on there. Okay? So what we are doing here, essentially we are expressing everything that we have as a perpendicular force and as a force that is acting on the body. Okay? Then next it's maths, literally just mathematics. You can choose whether you want to calculate your values for your cos 30 and your sine 30 just yet, or you want to wait all the way to the end. It doesn't really change much. I feel like it just changes one or two values. So cos of 30, if you plug that into your calculator, I get 0.866 F. Then on here, 80 minus sine 30, plug it into the calculator, I get 0.5 F, still multiplied by 0.25. Okay, then I try to simplify it, make my life easy, hopefully yours too. These cancel out, right? 0.866 divided by 0.25, I get a 3.464, still in terms of F. Then since we have removed the 0.25, the bracket has fallen off. Okay? Then we'll bring the 0.5 to the other side, so 3.464 F plus, remember now it's crossing over the equal sign, so the sign changes, as equals to 80. So 3.464 plus 0.5, I get a 3.964, still in terms of F, is equals to 80. Then divided by 3.964, divided by 3.964. So your F would be at 80 divided by 3.964. I get a 2.181 newtons. And that's essentially the force that would be required to pull the body across the surface. You are pulling it. So if you are pulling it across the surface, that would essentially be the force that you would need to apply. Okay? But this is just part A. This is just part 1 of the question. We are pulling. We're pulling. Right? So now I'm just going to try part B on the side. So part B says calculate the forces required to push if you are pushing the body across the surface. So just hope I remember what's going on here. You have your body on a flat surface, mass 80 newtons that's been exerted, and this time we're pushing it. It's still at an angle, so this would be your parallel, still at an angle of 30 to the horizontal. That's still there. That's your force. Okay? And since it's pushing it in that direction, it means your friction will be in the opposite direction. So frictional force is pushing back, it's fighting. Okay? Our frictional force is still in the same direction because essentially, in my example, our body is moving in the same direction even though the force is being applied or applied in different ways. Okay? Then step 1, components. Okay? So we can express it over here, and by now I think we've found a quicker way of expressing our components. But if we haven't, remember that's our SOHCAHTOA, right? And since our angle is here, we're essentially trying to express y and x in terms of our angle 30, right? We're trying to essentially, yes, okay, I'm repeating the same thing. Yes, we're trying to express x and y in terms of our 30. Now, using our sine, cosine, or tan, you'll decide which of those formulas will incorporate your hypotenuse, which is your f, and either x or y. So our sine allows us to solve for the y, and our cosine allows us to solve for the x, right? So if you say sine of 30, opposite over hypotenuse, your opposite is your y, hypotenuse is your f. So when you plug and play, cross multiply, your y will be f sine 30. Similarly, your cos of 30 is your adjacent over your hypotenuse, which is your x over your f. So if you cross multiply, your x is your f cos 30. Okay? Alright, looks like I'm writing with my foot. Let's try that again. F. Okay, it's getting even worse. I think my pen thingy's battery's dying, but anyway, bear with me. Okay, so now we have our components. So our x, we can just plug it back on there, is our f cos of 30, and our y, we just write it on there, is our f sine 30, not our sine. F sine 30. Alright. Step 2. Wait, is that step 1 or step 2? Is everything gone? Oh, it's on this side. Sorry. Okay, so step 1, you sketch. Step 2, replace the forces with components. Oh, we're actually on step 2. Step 3, we now go to our formula. Okay. Step 3, our formula. Frictional force is your perpendicular forces times your coefficient of friction. Okay. But that we know is 1/2 of the equation, right? So we'll say forces acting on the body should be equal to forces that are resisting the movement. So forces that want to push or pull versus forces that are saying a win down are equal. Okay? Then from that point on, we now go back to our diagram. All right? So on our diagram, wait, that's our frictional force. I don't know why it's not there. Okay, on our diagram, our force is pushing the diagram. Okay, so what's pushing? Pushing it will be this. Okay, we need another diagram. Because now we no longer need to consider the slanted force. We are essentially considering the force that is pushing your F cos 30, pushing it directly. Then the force that is going against that would be your frictional force. That is fighting with your pushing force. It's keeping the body in the same position, right? Those are the forces that are acting on the body. And then we have our perpendicular forces, right? The first one would be your perpendicular component, your F sine of 30. It's acting over here, but I feel like now I'm gonna mess up my stuff. Ugh. Okay, let's put F cos 30 here. Then we have this one, your F sine 30. It's acting now perpendicular to the surface. It's essentially exerted perpendicular to the body. And then we have the 80 Newton mass of the body, which is now acting perpendicular to your surface. Okay, I hope the wording doesn't confuse you guys. So now we need to plug this situationship we have here, the love triangle or love square, we need to plug it over here. Okay, so forces acting on the body, let's go back one more time, and we can assume that it will be pushing it to the right, so positive to the right. Okay, so the very first force that will be acting on it, it's our F cos of 30. Is there anything else that's acting with it? We'll say no. So the force acting on it, or force that's trying to move it, should be fighting with the force that wants to keep it in the same position. Okay, sharp, no problem. Then now we need to consider our frictional force. And our frictional force, we have this equation. Okay, so now we need to express our frictional force in terms of the perpendicular forces times the coefficient of friction. Perpendicular forces, we have the AT, and we can assume that downwards is positive as well, right? Then on here we can say we have our AT positive because downward is positive, plus that vertical component, our F sine 30, times our coefficient of friction. Okay, then our F cos of 30, and essentially we will carry out the same maths. Okay, I just changed nothing on there. It's a waste of space, my friend. Okay, cos of 30, plug that into your calculator. I get 0.866 F. 80 remains 80. Sine of 30, that gives me 0.5 F. All of that still multiplied by 0.25. Okay, then 0.866 F. We can divide everything by 0.25. Okay, that's looking messy. Divide by 0.25. Divide by 0.25. This cancels out. 0.866 divided by 0.25 in your calculator. 3.464. It looks like everything is going in the same route, except pay attention to the sign difference that we had on there. So that will be plus, wait, 80 plus 0.5 F. Okay, then 3.464 F minus 0.5 F, because now it's crossing over the equal sign, is equals to 30. Okay, then I have 2.964 F is equals to 80 divided by 2.964 on both sides. Then our F would be 26.99 newtons. And since we assumed that it's pushing it to the right, the fact that it gives us a positive sign means it is indeed pushing it. Okay, I hope this was clear. If you have any questions, you know what to do. I will be attempting another example in the next video. Until then, cheerio.